Today we are going to learn about mastering robot path planning algorithms. We will explore the fundamentals of path planning, implement basic techniques, and understand how to ensure efficient and collision-free navigation in dynamic environments. Welcome to our journey into the world of robot path planning algorithms. In this introductory segment, we will define path planning and discuss its crucial role in robotics. Path planning is the process by which a robot determines how to move from one point to another, avoiding obstacles and ensuring efficient navigation. It is an essential aspect of robotics as it directly impacts the effectiveness and safety of robotic systems operating in dynamic environments. We will explore the challenges faced in path planning, such as dealing with unknown terrains, dynamic obstacles, and the need for real-time decision-making. This video will cover popular algorithms like A and Dijkstra, and delve into their practical applications in real-world scenarios. Now, let's explore some of the most popular path planning algorithms that are widely used in robotics. We begin with the A algorithm, known for its efficiency and accuracy. A works by using heuristics to evaluate paths and choose the most promising one. It's particularly useful in scenarios where you need to find the shortest path quickly. Next, we have Dijkstra's algorithm, which is used to find the shortest path between two nodes in a graph. Unlike A, Dijkstra's does not use heuristics, making it more suitable for environments where accuracy is paramount over speed. We will compare these algorithms, discussing their advantages and potential drawbacks. For instance, while A is faster, Dijkstra's can be more reliable in certain static environments. Understanding these algorithms will provide you with the tools needed to choose the right approach based on specific use cases.
Graph-based path planning is a fundamental concept in robotics, utilizing the principles of graph theory to map out paths for robots. In this block, we'll delve into the basics of graph theory, focusing on nodes and edges, the building blocks of graphs. Nodes represent waypoints or locations, while edges indicate the path or connection between these nodes. Creating a graph allows robots to visualize their environment and make informed decisions about the best path to take. We'll discuss how to construct graphs for different robotic scenarios and examine various graph search techniques like depth-first and breadth-first search. Understanding how to apply these techniques in real-world applications, such as autonomous vehicles or robotic vacuum cleaners, will enhance your ability to implement efficient path planning. The Robot Operating System, ROS, is a flexible framework for writing robot software, offering tools and libraries for complex robot functionalities. In this segment, we'll guide you through implementing path planning algorithms within the ROS environment. We'll start by setting up a ROS environment on your system, ensuring you have all the necessary components installed. Then, we'll integrate popular path planning algorithms, such as A and Dijkstra, into ROS to simulate robotic navigation. Detailed steps will be provided to help you visualize how robots process path planning data and execute their movements. Additionally, we'll cover how to test and debug your path planning implementations, ensuring they function correctly within ROS simulations. By the end, you'll have a solid foundation for developing and testing robotic path planning solutions in ROS.
One of the major challenges in robot path planning is dealing with obstacles and dynamic environments. Obstacles can be static, like furniture in a room, or dynamic, such as moving people or vehicles. In this block, we'll explore various obstacle avoidance techniques that enable robots to navigate safely and efficiently. We'll look at how sensors and real-time data processing allow robots to detect and react to changes in their environment. Understanding the differences between static and dynamic environments will help you design path planning algorithms that can adjust paths on the fly, ensuring safety and efficiency. We'll also discuss the importance of integrating safety considerations into your path planning strategies to prevent collisions and ensure smooth operation.
Optimizing the efficiency and safety of robot paths is crucial for effective robotic operations. In this segment, we'll discuss various metrics used to evaluate path efficiency, such as travel time, energy consumption, and safety margins. Balancing speed and safety is a key consideration, as faster paths may compromise safety or increase energy usage. We'll explore techniques for creating energy-efficient paths that maximize battery life and minimize operational costs. Advanced optimization techniques, such as genetic algorithms or machine learning, can further enhance path planning by automatically adapting to changing environments. We'll provide practical examples of how these optimization techniques can be applied in real-world scenarios, enhancing your ability to develop sophisticated path planning solutions. Heuristics play a crucial role in path planning, offering a way to speed up decision-making by using rules of thumb or educated guesses. In this block, we'll explore various heuristic methods used in path planning algorithms, such as the A algorithm's use of heuristic functions to estimate the cost of the goal. We'll discuss the pros and cons of using heuristics, noting that while they can greatly improve efficiency, they might not always guarantee optimal solutions. Understanding when and how to apply heuristics will enable you to enhance path planning performance in scenarios where speed is more critical than precision. We'll also look at common heuristic algorithms and provide examples of their applications, helping you decide when heuristics are the right choice for your path planning needs.
Let's explore some real-world applications of path planning algorithms in robotics. Autonomous vehicles rely heavily on path planning to navigate safely and efficiently through traffic, avoiding obstacles and adapting to road conditions. Robotic vacuum cleaners use path planning to optimize cleaning routes within a home, ensuring complete coverage while avoiding furniture. Drones and UAVs implement path planning to execute complex flight paths, whether for delivery purposes or environmental monitoring. In industrial settings, robots use path planning to navigate factory floors, transporting goods and avoiding human workers. We'll delve into several case studies that highlight innovative uses of path planning algorithms, showcasing how these techniques are applied in various industries to solve complex navigation challenges. As we conclude our exploration of robot path planning algorithms, let's recap the key concepts covered. We've delved into the fundamentals of path planning, discussed popular algorithms like A and Dijkstra, and explored their implementation in RAS. You now understand how to handle obstacles, optimize path efficiency, and apply heuristic approaches. These skills are crucial for developing effective and safe robotic systems. We encourage you to continue practicing these techniques and explore further learning resources to deepen your understanding. Path planning is an evolving field with endless possibilities, and your expertise will be invaluable in creating innovative robotic solutions.